Our next talk, Data Science Delivered Continuously, is going to be presented by Arif. Please welcome him.
Hi. Test, test. Hi, everybody. Can you hear me through the mic? Great. So, thanks a lot for joining this session. I'm Arif. I'm from ThoughtWorks Germany. I'm a dev there. And yeah, I'm actually really happy to be here at the India Away Day. I really enjoyed the experience, and also lots of thanks to the great organization so far. So this talk today is basically an experience report about how we built a vehicle price estimation tool at AutoScout24 and what we learned from it. So some context about the client. AutoScout24 is one of Europe's largest online marketplaces for new and used vehicles. And they have roughly 2.5 million listings on the platform. And that actually means that they have a lot of data about how those cars are bought and sold and for which prices. So therefore, our task was to do something useful with all this data and to turn this into a consumer-facing data product where users can quickly estimate the current value of their car. And this works as follows. So the page is in German. We built it for the German company. So on the first page, the user puts in basic information about his car, like the make and the model and the year of first registration, and then fuel type and power, and then importantly the mileage, because it's mainly about used cars. So really just a few basic information about the car. And then on the next page, the user can optionally indicate some further equipment that the car has or what the condition of the car is. And then on the next page, the user gets immediately a price range where we estimate what this car is still worth. And this comes from a prediction model. So what we had when we started working on this was only the prediction model, because that's what the data scientists at AutoScout had already built. And the language that they used for building this was R, pretty popular in data science today. And the approach or the algorithm they used for it is called random forest. Does anybody of you heard of random forest already? See a couple of noddings. All right. So let's have a look simply of how this works. So the data of the last 2 years of all car listings on the platform is taken and is then used to train a prediction model. And what gets out of this training are many of such decision trees here. Yeah, and I mean, you see this decision tree is a hierarchy of decisions. And so, for instance, here, this whole tree is for the model Volkswagen Golf. And here the first decision is whether it has a mileage of more than 50,000 kilometers. And then you could go right or left. And if you go yes, then it's about the fuel type. And at some point, you get a price. And now the random forest algorithm is basically the algorithm that decides which of those decisions are the most important, and thereby decides about the order, how they are arranged in this hierarchy. And beyond that, and that's actually why it's called random forest, many of those decision trees are generated. And this is a technique to work against overfitting. Overfitting means that the model that you trained really only works for the data you train it with and is not a generally applicable model. And by creating a lot of those decision trees, you avoid having this situation. All right, now, so that's basically what data scientists do all the time, right? They build models from existing data. However, now, our task was actually to turn this model into a high-performance web application. And in fact, this is not such a common situation yet in the context of data science, because pretty often such data and such prediction models are mainly used for internal decision processes, like estimating user behavior or planning ad campaigns or so on. But yeah, if you want to create an actual user-facing application that goes out in the internet, then you have a very different situation, and you have to deal with things like load peaks, response times, and so on. And that was actually also one of the reasons why we ruled out to run an R server in production pretty early. Because the problem here is that R, at least in its open source version, does not support any multi-threading, and therefore it makes scaling for many concurrent requests pretty difficult. So yeah, how to turn this model into a web application then? A pretty traditional approach here in such a situation where you need the performance and the scalability is that basically the prediction model, which has been developed by data scientists in their favorite language, such as R, is then manually translated by a software engineer or a group of software engineers into a comparable prediction model implemented, for instance, in Java in order to tweak it for performance and to integrate it well into a web application. However, now, with this manual approach, what do you do if the internal structure now of that prediction model changes, or the data scientists come up with a new approach or use a new algorithm? Now basically the software engineer or the group of software engineers has to re-implement this translation here to Java. And not only does this take quite long, but also a lot of mistakes can be introduced here. So that basically in the end, this Java-based prediction model does not behave anymore exactly the same way the data scientists actually intended it to do. So we therefore looked on how we can automate this. And the technology that helped us with that was H2O. And has anybody heard of H2O before? Okay, cool. H2O is a Java-based analytics engine that can be programmed using R, and that's obviously something that the data scientists liked. And that was actually the important piece for us. It provides the possibility to export your fully trained prediction model to Java source code. So basically to generate this Java-based prediction model here for us automatically. And this, in the end, allowed us to integrate then this automatic model generation into a continuous delivery pipeline. So let's have a look how this looks. So first of all, here we have the base data. This is the historical data. And then this is taken as an input for, in our case, an R script. This is what the data scientists were writing. And this uses the random forest implementation of H2O to train the model. And of course, in here, there's also data cleansing and other steps and so on. And then out of that, you get the trained model, which is still in an H2O format, basically. And then, as the next step, Java code is generated, Java source code, which is then compiled into a jar. And this is then uploaded to AWS S3 because our whole application is based on AWS. So this is the prediction model pipeline. Now, whenever something is changed in this R script, which is taking care of the model basically, and that's at least as important, whenever the base data changes drastically, automatically a new model is generated and automatically uploaded to S3 here. All right, now for the web application, which we implemented in Scala using the Play framework, there's another continuous delivery pipeline. And this pipeline also generates a jar, the application jar. And now this jar is deployed to AWS EC2 to run the actual application. And now, whenever we deploy this web application here, this pipeline here actually pulls in the newest prediction model from AWS 3. And, at least equally important, whenever a new model here in this prediction model pipeline is created, it also triggers a redeployment of the web application. And this way, all prediction model changes made by data scientists go straight to production, and users can thereby immediately benefit from it. However, this automatic deployment to production, make it user-facing, only works if you have enough confidence to do so. And therefore, we built an extensive model validation workflow. And let's start here with how a model is usually trained and how the success of the training data, of the training is evaluated. So you, in case you're a data scientist, you divide the existing historical data into training data and into test data. And those sets, they need to be disjunct. And then the model is trained using this training data, and out comes the trained model. And now the test data is used to create test estimations. And that actually means that from this test data here, we take only the input data, such as how old is the car, what was its condition, what model, and so on, and then ask for that specific input data, the trained model, and we get out an estimation. And then we compare this test estimation with the actual price that is here in the test data, because we know what the ideal result is, right? It's in the historical data. And then, of course, those two things, the test estimation result and the actual expected result, will never be exactly the same. But this is a really good way, in this case, to measure the quality of the model and also to monitor it over time. And of course, here you also now understand why those two sets need to be disjunct, and you must never use test data to train the model, because if you use the test data to train the model, then those test results will be perfectly accurate, but yeah, you haven't tested how the model will actually work with new data that it's not trained with. Oh well. So further down the pipeline, we use these test estimation results here for a pretty comprehensive end-to-end model validation. And that means that here we generate this Java code, and here we create this jar out of it. We use, again, those same input test data from this bucket here, and now ask in this test estimation validation here, ask actually our composed system in the JVM using that compiled model here, and then check that we get exactly the same results that we got here. And this way, we make sure that we, like through all those steps, we haven't changed anything in how the model behaves, right, and how it's integrated into JVM and so on, so that we really make sure that our model and our application in the end, which will be live, is really doing what the data scientists expect that it does. And then, furthermore, we also check whether this model fulfills all the expectations that our web application poses on it. And this is called a consumer-driven contract test. And in this case, our web application is the consumer of this model. So the web application basically describes its expectations. And this is also automatically tested. So we really make sure that those two things, the application and the model, still fit together. And yeah, and only if all those things are green, then we automatically release to production. All right, so then let's already sum up a little bit and see what we learned from this. So first of all, we learned that it's important that you form cross-functional teams of data scientists and software engineers. And that's really important. So we didn't start that way, so it was also a bit tricky organizationally. But if you have two separate teams, data engineers and of data scientists, you will always wait for each other. Like you build the web application and you want something to change in the interface of the model, and then you wait for the data scientists and the other way around. So it's really crucial to come together as one group, as one team, and it's going to be much faster, and you will learn a lot from each other. The data engineers, they learn how the model training works, and the other way around. In our case, it was really cool that the data scientists learned a lot about continuous delivery, testing, and so on. Then second, set up usage reporting really early in the process in order to be able to improve your data product in a data-driven way itself. We should have also done this even earlier. That means that you really measure or collect the data about how your data product is used by users, and then make this accessible to the data scientists again, so that they can continuously improve on the product. So yeah, you should be data-driven yourself as well. And then finally here, this is a technical lesson learned. Basically, in our situation with the random forest and H2O, we were generating gigabytes of Java source code. And this is a challenge, if not even an abuse of the JVM. This basically means it's a very specific usage scenario. So we use very little heap space, but we use gigabytes of meta space. And therefore, it was crucial that we use, for instance, the G1 garbage collector, which is now standard, but wasn't standard by then, because here you can define the maximum amount of time a garbage collection sweep takes. Because if you don't do so, your web application can become unresponsive for a while when the garbage collector goes through all this meta space. Second, do extensive warm-ups in this situation, because the JVM is pretty smart and only loads into memory what it actually uses. But if it really only loads this into memory at the point when it uses it, then again, the web application can become unresponsive. So if you have such a large model to run into JVM memory, then you have to warm up with a lot of cases to avoid this situation. And we actually also integrated this in the continuous delivery pipeline. And then finally, we learned that you have to turn off tiered compilation. Again, that's a really smart feature of the JVM. It optimizes continuously on the fly the machine code that is generated. But again, with such amounts of source code, this can make the web application suddenly very unresponsive. All right, so let's come to the few conclusions. Generally, it was really successful to apply continuous delivery to this situation, and it allowed us to bring prediction model changes live very quickly. So really, the data scientists change something, and it goes straight to production, and it's live. However, really only extensive automated end-to-end tests provide the confidence to deploy to production automatically, and I've shown you a little bit about this. And then finally, this Java code generation approach that we went for allows for very low response times. We're really talking about 2 to 5 milliseconds response times of the service. And excellent scalability for high loads, because it's all in one JVM. It can all be managed on AWS, and you can basically use all the means that you have for scaling. But as I said, it requires a lot of memory, and you have to deal with this. All right, that's it. So thanks a lot, and I'm really happy to answer questions if we have time. Do we have time? All right.
So how often did the pipeline break, and how difficult it was to understand why the model was no longer good?
So let me repeat the question quickly. So it was asked how often the pipeline broke and how hard it was to find out why the model basically changed, right? So in fact, the pipeline usually broke because of other reasons. So usually the CDC test that I mentioned was really important because there we clarified the interface. I think the reason it broke most often was that something in the interface, like some spelling or so in the interface actually changed. With the thing that the model quality deteriorates, we didn't have that problem so much because for us in this situation, the data that we get in is actually the truth, right? So, so we actually have the right prices, and thereby we can really check how it compares to the actual price. So we really didn't have that situation so often. It broke out of other reasons really often, but those were mainly about the interface or internals being changed.
Thank you.
You're welcome. Yeah,
Thank you, Arif. I'm sure there are a lot of questions amongst the audience, but please, if we can take that offline, that would be great. Thank you
All
so
right.
much.
Thank you very much.